Okay, so this is 8.3 part 2. So we are continuing to solve systems of linear equations using matrices. In the previous video, we used Gaussian elimination to get our matrix into row echelon form, where then we used back substitution to finish solving for the variables that are in the system. So now we're going to look at using Gauss-Jordan elimination, so where we basically just go a couple steps further, still using row operations to get the matrix into reduced row echelon form. Okay, so for solving this system of equations, three variables, the first part is of solving this using Gauss-Jordan elimination is going to look very similar to using Gaussian elimination. So I'm going to start by writing the matrix as an writing the system as an augmented matrix. And my first goal is to have this, get this augmented matrix into row echelon form. So we already have a 1 in row 1, column 1 position. So let's use row 1 to help us get 0, make the 3 into a 0 and the 2 into a 0. So we'll do row 2 minus 3 times row 1 to replace row 2, and row 3 minus 2 times row 1 to replace row 3. So nothing's happening to row 1 yet. Row 2 will now be 0, and I wrote y instead of 1. Okay, so we'll do 1 minus 3 times 1 will be negative 2. Negative 1 minus 3 times negative 1 will be positive 2. Negative 4 minus 2 times negative 3 will also be positive 2. So now row 3, we'll have 0. Negative 2 minus 2 times 1 will be negative 4. 3 minus 2 times negative 1 will be 5. And then 3 minus 2 times negative 2 will be 7. Okay. So next I want to get this negative 2 to be positive 1. So I'm going to multiply row 2 by negative 1/2. And I haven't touched row 1 or row 3 in this step. Okay, so now I can use row 2 to help me get negative 4 to be 0. So we'll do row 3 plus 4 times row 2. Okay, so this will stay 0. This will become 0. 5 plus 4 times negative 1 will get 1. Oh, that's nice. And then 7 plus 4 times negative 1 will be 3. Okay, so at this point, we're actually in row echelon form. But we want to go further to reduce row echelon form. So we're going to need to now kind of work our way back up to make these guys into 0. Those elements into 0. So I'm going to use row 3 to help me make negative 1 in row 2 equal to 0. And I'll do that by doing row 2 plus row 3 to replace row 2. -1 plus 3 will be 2. Okay, so right now I can actually see what y and z are equal to. Y is equal to 2, z is equal to 3. We're almost there. Let's use row 2 and row 3 to help us. So row 1, why don't we subtract row 2 and add row 3. You could do this in 2 different steps, but by subtracting row 2 from row 1, that will make the 1 in column 2 equal to 0. And then by adding row 3, that'll make the -1 become 0. Okay, so -2 minus 2 would be -4, and then plus 3 would be -1. So now we are in reduced row echelon form, where we can see we have this diagonal of 1s, 0s above, 0s below the diagonal. So our solution, we end up with x equals to -1, y equals to 2, z equals to 3. If we represent our solution as an ordered triple, -1, comma 2, comma 3. Okay, so inconsistent and dependent systems. So far, using matrices, we've only solved systems that were independent, meaning there was exactly one solution. So one point of intersection of either the 2 lines or of all of the planes if they're equations with 3 variables. But we've looked at independent systems. So basically, there's going to be one unique solution if the diagonal entries are all 1s and 0s occupy all the other coefficient positions once you get to reduced row echelon form. And that will look like so, like our last example. Okay, or I can just say 1, 2, 3 for x, y, z. Okay, so if you're able to get the diagonal all 1s, and then all of the other elements to be 0. Now you're going to have an inconsistent system if, when going to reduced row echelon form, you get 1, 0, 0, maybe 0, 1, 0, and then let's say this last column for a 3 by 3 is 0, 0, 0, and then we still have 1, 2, 3 over here. The bottom row has 0 for coefficients for x, y, and z. So it's basically saying that 0 equals to 3, and that's not possible. So this is an example, or this is how you would know that the system is inconsistent. If you get a row in the bottom of the matrix where the left-hand side is all zeros, but then you have some other constant on the last column. And you have a dependent system if one row will be entirely zeros when the number of equations equals the number of variables. Okay, so like if we had 3 equations, 3 variables, and we went to reduced row echelon form, we would have 1, 0, 0, 0, 1, 0, 0, 0, 0, and then maybe 1, 2, 0. Okay, where we just end up with a row of all zeros. We would know that there's a dependent system. Okay, so let's try solving this system, which we can see it's telling us it's going to be inconsistent, but let's see what that looks like. So first, writing the system as an augmented matrix. All right, we already have 1 in row 1, column 1. That's good. So let's use row 1 to help us make the elements in row 2, column 1, and row 3, column 1 also 0. So we can do row 2 minus 2 times row 1 to replace row 2, and row 3 plus 2 times row 1 to replace row 3. One minus 2 times 2 will be -3. 2 minus 2 times -1 will be 4. And then -1 minus 2 times 3 will be -7. For row 3, -2 plus 2 times 1 is 0. -4 plus 2 times 2 will be 0. 2 plus 2 times -1 will be 0. And 5 plus 2 times 3 will be 11. Okay, so right here in the bottom row, we ended up with all zeros on the left-hand side, but we ended up with a constant on the right-hand side. So what this would be really saying is 0x plus 0y plus 0z equals to 11, which is just 0 equals to 11, and that's not true. So we can tell now that there is no solution to this system. It is an inconsistent system. Okay, so determining a system is dependent. So first, write as an augmented matrix. Notice that there's no y in the first equation, so the coefficient for y is just going to be 0. You have to put that in. Okay, using row 1 to help us make 2 and 3 zeros. Let's do row 2 minus 2 times row 1. And row 3 minus 3 times row 1. Okay, so 0. And then 1 minus 2 times 0 will still be 1. 4 minus 2 times 1 will be 2. 8 minus 2 times 3 is also 2. Okay, we'll stay 1. 5 minus 3 times 1 is 2. Wait, 5 minus 3 times 1 is 2. Yes. Okay, and then 11 minus 3 times 3 is also 2. Okay. So if we were to try and use row 2 to help us make the element in column 2 and row 3 0, if we did row 3 minus row 2, we can see what's going to happen. We just end up with our row of all zeros. So here we can tell there's going to be infinitely many solutions. Okay, so basically all three of these planes are going to intersect in a line. We want to be able to represent the infinitely many solutions, or the entire solution set. So if we were to let z, if we were to let z equal to a, okay, row 2 represents the equation x plus 2y equals to 2. No, not x plus 2y. Silly. Sorry. Y plus 2z equals to 2. Where we can substitute a in for z. So y equals to negative 2a plus 2. And then in row 1, we have the equation x plus z equals to 3. So replacing z with a again, x equals to negative a plus 3. So our solution set can be represented as negative a plus 3, comma, negative 2a plus 2, comma, a. Where you can choose any real number for a, for z, and then find the x and y that go with that value for z. Okay, we talked about when we have a system like this, where we have 3 variables and 2 equations. This specific system, remember, when we have an equation of 3 variables, the equation represents a plane. So if you only have 2 equations representing 2 planes, those planes are either going to be parallel to each other, meaning there would be no solution, or they're going to intersect in a line, so there would be infinitely many solutions. So writing this system as an augmented matrix, we use row 1, so still trying to get to reduced row echelon form. So row 2 minus 3 times row 1. Negative 1 minus 3. Okay, and then if we were to, let's do R2 plus R1. Okay, so basically, because we end up with, actually at this second step, we would have been able to tell that there's infinitely many solutions. So because row 1 didn't just cancel out row 2, we can tell there's infinitely many solutions. It's a dependent system. You could keep going to try and simplify, but at this point, even at this point up here, we could tell that there are infinitely many solutions. So it's a dependent system. We can let z equal to a. Okay. And if I go back up to, I'm going to get rid of this matrix, actually. It's not very helpful. If I use row 2, that row 2 represents the equation negative y minus 4z equals to 2. So I could let z equal to a and solve for y. And then we could use row 1 to help us find what x is in terms of a. So that'll be 3a plus 2 for x. So our solution set can be represented as 3a plus 2 comma negative 4a minus 2 comma a. Okay, this is kind of like whenever you were if you were trying to solve this system using elimination, and here, let's do that. So let's say we added these two equations together. Oops. Okay, the z is eliminated because we ended up with something not like 0 equals to some other number. This means that this is a dependent system. So this is thinking back to section 8.2. Okay, so that is it for section 8.3.